Defeating Machine Learning, What Your Security Vendor Is Not Telling You with Bob Klein and Ryan Peters. If you could please put your phones on vibrate, silent, or turn them off altogether, it would be really appreciated. Those calls can just go to voicemail. Thank you.
Good morning. I know it's the last day of the conference. I'm sure many of you are nursing hangovers or, at this point, hunger. We appreciate you coming out. So my name is Bob Klein. This is Ryan Peters. Machine learning, right? Machine learning has become quite a buzzword, and many vendors are touting it as the ultimate defensive technology. And we should be excited, right? Machine learning is no longer relegated to laboratory experiments as some neat idea, but rather it's technology that's seeing use across many industries and many deployments with great success, right? And ours is no exception. And to give you a little bit of background of why we're interested in this, many of you may not be familiar with Blue Vector, but for over 5 years now, our particular team has been working to fine-tune a machine learning approach to file-based network threats. We've earned a lot of scar tissue in the process, but over these 5 years, we've been able to take our approach and operationalize it. In the last 18 months, we've actually instantiated dozens of deployments in the government and commercial space, ranging from several thousand end users to over 300,000 in a large deployment. And the point here is not to boast, but just to convey that we're painfully aware that simply applying machine learning to a problem does not magically solve it, particularly when attempting to make it viable operationally. So today we want to talk about some of what we've learned from our experiences and focus on a specific issue that machine learning fails to address as currently implemented. We'll talk about a solution and how we can implement it in general. So we'll start by reviewing the evolution of the security industry and how machine learning fits into it. We'll next demo what the security landscape looks like from an attacker's perspective and show how some machine learning approaches can be defeated using fairly simple techniques. We'll then review what went wrong as defenders and propose a solution that introduces significant uncertainty and risk to the attacker. We'll explore this new paradigm first in concept, then in practical implementation, operation, and finally in quantitative results. We'll then revisit the demo with the solution implemented and see how the landscape has changed from the attacker's perspective. And we'll conclude with additional impacts to the analysts and how we can apply this technique moving forward. So to begin with a quick review, this is basically what the security industry looked like 30 years ago, right? Early attackers did not need to work hard to wreak havoc, and so they didn't. Early solutions produced by the security industry were similarly basic, right? If we look at early creatures in this, so much like evolution, this sort of tit-for-tat adversarial relationship has persisted over the years. Early creatures in this evolution, such as our signature amoeba here, were very simple, right? Early malware detection engines, for example, typically looked for exact hash matches, and first-gen stateless packet filters were essentially limited to exact matching on source, dest address, port, and protocol. And while a major step forward from basically nothing, these solutions share a weakness in their total brittleness, right? This is apparent as adversaries evolved to evade AV signature-based detection, for example, by permuting even a single byte in their malware. So users and enterprises suffered attacks from such techniques and demanded better. And so once again, the security industry obliged, providing heuristics to detect common malicious indicators in samples, sandboxes to detect malicious actions taken by samples in execution, and so on. But once again, while a major step forward and a significant reduction in brittleness compared to previous solutions, attackers once again exploited these with problems with these as well. And so users and enterprises are now demanding additional protection, and the security industry has to evolve again to supply it. So where does that leave us today, right? So many vendors would say that we are here, right? That machine learning, this technology from the future, with a power that may mark the beginning of the end for humankind and on, solves all of our problems and is completely unbreakable, right? But in reality, we're probably a little bit closer to here, right? There's a lot of evidence that shows that the brittleness of these earlier approaches have been improved, and that the learner can generate rich and robust descriptions of malware, for example. So does this make sense? Imagine, I think it actually helps to introduce an analogy actually to explain what we mean by this. So imagine each user or enterprise as a building, right? Some are big and some are small, but all want to keep malicious actors out, right? And here I'm just going to explain sort of what the issue is with machine learning, right? So we have these houses, and everyone wants to keep malicious actors out. So they go to this town lock store, let's say, and buy a lock, right, which represents our security solution. as a malicious actor, we're looking to break into one of the juicier targets, say one of the bigger office buildings. And we can ensure a swift, silent, and undetected entry by knowing how to break the lock before we show up, right? But under the most common signature-based deployment paradigm, all environments receive identical signatures, right? In other words, the locksmith sells identical locks to everyone. Each building is protected by an identical lock. And in most cases, a malicious actor can even just go to the lock store and buy a copy of the lock himself. And if he can't, and he's dedicated, which he probably is if he's going after one of those bigger office buildings, he can obtain one through other means. He takes the lock to his basement, spends as much time as he wants picking the lock, free of risk or time constraints. And when he figures it out, he strolls right up to the locked office building and walks inside, right? So this image should be terrifying, right? The point is that in the security space is that an attacker can easily verify that his exploit works against a target protected by such a solution. Because all deployments are identical, all he needs to do is obtain any copy of the signature-based product and iterate against it, and hone his exploit until he knows it will be defeated, right? So, and here we have the attacker, right, with his lock. But those were early solutions, right? What about newer heuristic approaches and sandboxes, which we represent by the stronger lock here? And unfortunately, we see a very similar picture, right, where each deployment is the same. The malicious actor can obtain a copy of the heuristic engine of the sandbox software and iterate until he goes undetected, right? And note that in all cases, this is done without any detailed reverse engineering of the inner workings of the security solution, and merely testing against it is enough. And so we've seen that this is this thread of this common issue that's persisted through many of these different technologies, and so we ask, what then about machine learning, right? And unfortunately, what your security vendor may not be telling you is that some flavors are quite susceptible to this type of attack because they rely on the same flawed deployment paradigm. But to really answer that question, we need to be a bit more specific about what we mean by machine learning, right? And to do that, we'll just take a quick look at how machine learning has been applied across the security industry and identify areas where the shared deployment paradigm is an issue. So different security niches have found different types of machine learning to be particularly suited to their applications, right? And the reality is that not all of them suffer from the same weaknesses. There's a lot of different ways to slice the machine learning cybersecurity pie. We'll be using this one here, where we distinguish between incremental algorithms, which continuously integrate new data, versus batch algorithms that need to be trained all at once, right? We'll also distinguish between supervised algorithms, which rely on data labeled with ground truth, and unsupervised algorithms, which essentially attempt to find structure from otherwise unlabeled data. When you think of unsupervised algorithms, you typically think of something like clustering. So here are a few examples of some of the security applications that have used, in this case, unsupervised incremental algorithms. So most of these attempt roughly to build a profile of what normal looks like over time, right? And that's the incremental piece, continuously using this data to figure out this sort of normal profile. And the unsupervised piece, you can imagine that there's sort of this cluster of what we think normal looks like. It's used to identify departures from normal, right? Anomalies. Network traffic profiling, spam filtering typically use these supervised incremental algorithms. I'll use spam filtering as an example. Many of you are probably familiar with this. Users receive emails and label them as spam or not spam. And so again, that's the supervised component. We have labeled examples. And then a machine learning algorithm can continuously integrate those samples and ideally learn something new about what spam emails look like. The task of clustering malware into families, I actually just said the word clustering, so a good use for an unsupervised algorithm. And it's often done in batch on large fixed data sets of malware. And then lastly here we have malware detection has almost exclusively relied on supervised batch algorithms. Training is often done all at once on large fixed corpuses of known benign and known malicious data. So with this sort of high-level image of how machine learning has been used in the security industry, we can return to this problem that we identified before of these sort of shared models that are distributed to everyone. We note that this lower right quadrant is particularly worrisome. Malware detection solutions are widely deployed, yet training is often done exclusively in batch by the vendor, which then pushes out identical models to everyone. So we'll focus on this piece for the remainder of the talk, starting with a demo from the attacker's perspective on how this deployment paradigm is fundamentally flawed. Right? We'll see if a malware author in possession of a copy of the shared model, the machine learning model, is able to defeat a target. And so for that, I'll turn it over to Ryan.
So I'm going to briefly describe the experimental setup that we're going to use for our demo. So the general workflow we're going to be using is very simple, as the goal of this demo is to visualize a concept, not a specific exploit. First, we will generate payloads using the Metasploit framework. Next, we will iterate on how we encode these payloads. These iterations will vary the encoders that are used and the number of passes of each encoder. In addition, many of the encoding methods involve some sort of standard randomness. We will then embed these payloads in a standard Windows calc.exe template and deploy the variant against target environments running Windows 7 to measure effectiveness. Our method of deployment to the targets will be a simulated spear phishing attack. The two Metasploit payloads we are using for this demo are the Meterpreter reverse TCP, in which when the binary is executed, it connects back to the attacker to create a reverse Meterpreter shell, as well as the message box payload, which displays a message that pops up when the binary is successfully executed. Now, obviously, a malicious actor would not announce they've just gotten into your system, but we're going to use this for demonstration purposes only. So the presence of both of these activities will be used to indicate a successful exploitation. For our antivirus software, we're using ClamWin because it is free and open source. However, we will also mention later the effectiveness against an aggregate of antivirus engines and VirusTotal. For the machine learning software, we generated a model for this experiment that was trained on 20,000 benign and 20,000 malicious samples. The performance of the classifier on the files we did not train on is shown below. And we're using two main metrics to measure our performance. The first is the false positive rate. And these are the benign events that were incorrectly marked as malicious. And these are events that cause particular heartache for analysts who must review these events as though they were malware. And particularly when transitioning away from a signature-based approach, which has nearly zero false positive rates, is a challenging feature of all probabilistic detection approaches, as a subject we'll revisit later in the talk. The second metric is false negatives. And these are the malicious events that were incorrectly marked as benign. In other words, these are the malware that would have slipped through your defenses undetected. So the performance numbers are sub 5% for both the false positives and false negatives, indicating this is a reasonably performing classifier. For this demo, we are going to make two main assumptions. The first is the attacker has obtained a copy of the AV and the ML software. And the second is that the attacker does not have access to the exact signatures or the model itself. In other words, they have not been able to reverse engineer the signatures of the model, but are instead treating the software as a black box. So now we'll transition into the first demo. So we start in the attacker's lab, where the malicious actor is running a variant of Linux with the Metasploit framework. First, we are going to run a script to generate the two payloads, the Meterpreter reverse TCP and the message box. We then add these payloads without applying any encoding to our calc.exe template. Since we are going to be simulating a spear phishing attack as a way to deploy these files to our target system, we will move the new unencoded variant to our local HTTP web server. The attacker then opens up a multi-handler using Metasploit to wait for a C2 signal if the malware successfully executes. In this case, we have set up a fake domain name called myfreecalc.com. So on the target Windows 7 box that's running the antivirus, we're going to click on the spear phishing email to download it to our local system, and we're going to scan the binary using ClamWin. And as we see here, ClamWin did successfully detect the malware. We can perform the same demonstration on our target Windows 7 system running our machine learning model. And as we will see, the machine learning model also successfully detects the malware. So it's important to note that a malicious actor would not typically deploy their malware at this stage. However, we are just showing this to establish a baseline for the remainder of the demo that both the antivirus and the machine learning solutions detect the Metasploit-generated malware using only unencoded payloads. We can now try the simple idea of applying a single pass of Shikata Ganai to the payloads before inserting it in our calc.exe template. And Shikata Ganai is a polymorphic XOR encoder that is very commonly used as a first attempt in Metasploit to achieve AV evasion. As we did earlier, we will stage our new variant, generated with that one passive encoding on the payloads, in our local HTTP web server in order to continue our simulated spear phishing attack. In addition, we still have our reverse handler running on the attacker's box from earlier in the demo. So now let's see how this new variant performs against the antivirus. And as we can see, there was no detection by ClamWin. So let's try and execute it and see what happens. And we are now in. So let's pause for a few seconds. The first thing we see is the message box payload we added, letting the user know they've been hacked. We can also see on the left side in the attacker's environment that we successfully opened up an interpreter session with the target. So running sysinfo demonstrates the connection by displaying information about the target. And we can also open up a command shell and basically have complete control over that system. We can then test the same variant against our Windows 7 system that is running our machine learning model. So the main selling point for machine learning is that it is not susceptible to the brittleness of signature-based approaches. And as we see, the machine learning model still successfully detects the malware. Therefore, we now established that it does not take much work to defeat many antivirus solutions, but that machine learning is more resilient to these simple approaches. So what can we do to defeat the machine learning solution? How about we try what's been done in the past and iterate and see if we can find a random variant that manages to evade detection. So what we are going to do is run a script that in each iteration will create a new variant of the malware while varying the encoders, the number of passes, and also introducing a standard randomness into the binary. We would then automatically deploy it to a test virtual machine in the lab and attempt to execute it. The script then attempts to establish C2 with a remote machine. If the malware is blocked, the connection will time out, and the process starts again with the creation of a new variant. These iterations continue until a successful connection is made, at which point we have found our golden variant. So for demonstration purposes, we have sped up the script, as it typically takes about 20 to 30 seconds to generate each new variant. We obviously do not have time to run it in real time. And as you can see, it took about 1,900 iterations to find that golden variant, which took roughly 15 hours when we actually ran it in the lab. Again, we'll stage our new calc.exe on our HTTP server for our phishing attempt, and then we will then test the malware on our machine learning system, since we have already shown that we can defeat the antivirus solution. And again, we are in. So we see that familiar message box announcing our success, as well as an interpreter session that is successfully opened back in the attacker's lab. Running sysinfo shows that we're now pulling information from our machine learning box. And again, you can show that we can open a command shell. So the process took a lot longer than trying to defeat antivirus, but the reality is machine learning can still be defeated. So what went wrong? How did these deployments get owned despite one of them having advanced machine learning defenses? Well, if you look at the iterations of the malware in the attacker's lab, we can get a portrayal of what is going on under the hood. The antivirus solution is looking for an exact signature. It is not difficult to permute the file until that signature is evaded. In our summary chart here, we see that our antivirus solution we selected, ClamWin, was defeated with only one iteration. So while ClamWin is admittedly not a very sophisticated antivirus, the reality is 60% of all virus total engines would have been defeated with this one simple pass of encoding. And it's not difficult to defeat the other ones with more iterations or more targeted modifications to the malware. The machine learning solution, on the other hand, is looking at many different features in the file. Some are indicative of benign-ware, others of malware, depending on the context. And as the malware is permuted, the classifier keys on different features of in the file that taken together indicate a final classification. This makes it much more difficult to evade or for the attacker to figure out what is going on under the hood. But we see that it's still possible with iterations. In our demo, we showed that it took about 1,900 of these iterations to find a variant that defeated our specific machine learning model. So the reality is the attacker has two main advantages against the machine learning model that carried over from the antivirus deployment paradigm. The first is that they can be fairly confident that the model has not changed since they obtained their copy of the software. Many machine learning vendors go for months between software updates due to the resilience of the model against zero-day threats. And the second is they can be confident that all the targets have the same model. If you can defeat one copy of the model, you can defeat all the copies. So the main takeaway is if the attacker can obtain a copy of the machine learning model, all it takes is persistence to develop a variant that will succeed against every environment that has deployed that software.
Cool. Thank you. So I think it helps to return to the lock analogy for a minute here. Here's our previous example that shows our traditional malware detection engine, right? And so from what Ryan was saying, that all that's really different now is that there's basically a new locksmith in town, right? He makes new, really robust locks under the brand machine learning, and they really are better than the old ones. They're way more robust, and they're far less susceptible to lock picking, right? But guess what, right? He only sells identical locks too, right? They're all identical, super fancy locks. And so the malware author goes to the lock store, just like before, buys a copy of the lock, heads to his basement, gets some Mountain Dew, and spends as much time as he wants picking the lock. And once again, once he figures it out, he can stroll right up and basically walk inside, right? And some of you may still be a little bit skeptical. You're saying, no, Bob, my machine learning operationally deployed classifiers are far more advanced, right? And to some extent, you may be right? We trained a classifier specifically for this experiment. We didn't train on the data you're using for yours. We're not using the data that we use for our operationally deployed classifiers. But the purpose of this talk is not to be specific about a certain attack vector or talk about a specifically robust type of classifier, right? The purpose of this talk is not to show you that Metasploit can be used to defeat machine learning. As anyone familiar with the technology will tell you, it's simply not possible to achieve perfection, right? 0% false negatives and 0% false positives. And if you accept this premise, right, that some will always get through and that your classifier is not perfect and completely undefeatable, and frankly, it's naive to believe otherwise, then you accept that the malware author's job is simply to find one of those gaps in this target security solution, right? And to be one of those false negatives. And by using a shared defense, where our models are identical among all of our deployments, we make the task of finding one of those gaps for a dedicated attacker much easier, right? As any copy of the software will do to serve as a test bed for the real thing. And while we stated and showed that with model in hand, defeating a target through blind iteration is possible without reverse engineering, by no means does it preclude doing so. And you can imagine for some of the more advanced classifiers, you would want to be doing some form of more advanced reverse engineering to actually get through them. You can imagine an attacker in possession of the model, say sending in PE32 executables, for example, making a small change, perhaps changing a function call, sending it through again, and seeing how the classifier scores it differently for these small changes, and effectively through experimentation, reverse engineering a small relevant component of the classifier. So anyway, looking back at our picture, the situation is actually pretty scary when viewed from the attacker's perspective. And the problem appears obvious, right? It jumps out at you. And the solution follows naturally, right? And the answer is not just getting stronger locks, right? And I'll actually repeat that. The answer is it's not just getting stronger locks. And this is why we de-emphasized our use of Metasploit earlier, right? If you're hung up on one classifier being particularly stronger than another, you can really just look at this picture, right? I don't care if you're using a retinal scanner to protect your house. This is a systemic issue. So as a defender, the blind desire to obtain a stronger lock is an easy mentality to get into, but it misses this true landscape from the attacker's perspective, right? So as we said, obviously we work on machine learning ourselves. The introduction of machine learning for malware detection is a great thing. But right now, this is largely what it looks like. So I'm beating a dead horse a little bit here, but again, the answer is not just getting stronger locks. The answer is that people should be using different locks, right? And ideally, they'd actually change their locks once in a while. But as we saw when we were surveying the history of the security industry, new security technology did not arise directly in response to new attack vectors by malware authors in this case, but in response to a demand for defense against those attacks, right? So in this analogy, there's nothing technologically stopping the locksmith from producing different locks, but it's a pain in the ass for him to do, and no one is asking for it. So we'll speak to both of these topics a little bit later in the talk. Some of you may be familiar with the idea of a moving target defense in cybersecurity, which attempts to increase the cost and basically effort on the part of the attacker by changing the target's software and overall configuration. This changing attack surface adds uncertainty to the attacker's mission. So we borrow some of these ideas and introduce the idea of what we're calling a moving defense, where the security solution itself is changing both spatially across deployments and also temporally within a given deployment, right? So from an attacker's perspective, it makes our town look a lot less like the one on the left and a lot more like the one on the right. And if we include the temporal element, it actually maybe even looks more like this. But then naturally you'd ask, so why hasn't this been done before, right? This single lock paradigm for malware detection has been in place for decades, right? And while the moving defense is a simple concept, it's actually very, very difficult to implement in practice. For starters, it's a logistical nightmare, right? So as a vendor or a locksmith, how do you ensure that all of your locks are different and yet equally effective, and find a way to distribute them and maintain them, right? It's also very costly, right? And it's kind of a related issue. Vendors don't really talk about it because it's easier just to produce one lock or one model and distribute it to everyone. And this isn't so much what your vendors aren't telling you, but as why they aren't telling you, right? And lastly, why should the locksmith actually make multiple locks if it's so, frickin' hard? And he's worried that you're going to complain that if somebody breaks into your place, it's because of a particular lock that he issued. The latter is a legitimate concern too, and something worth discussing. But for the locksmith, it's better to just avoid this issue of multiple locks entirely. And so, crap, right? So where does that leave us? And what's interesting is that machine learning, while it's subject to this problem as it's currently deployed, is actually quite well suited to implementing a moving defense in practice. And as we'll show, this can actually be done in an operationally realizable way. We know that in this scenario, the attacker gains a huge advantage by having access to the model that's shared among all deployments before he actually goes after a particular target. So by altering the machine learning model so that it is unique for each deployment, we can achieve a moving defense. So this is cool, but we'll switch gears now and talk about how we can actually do that in practice. So in order to permute the machine learning classifiers, there are really three main knobs we can turn, right? The first is the feature space chosen. We haven't talked about this at all. We're intentionally trying to stay out of the weeds here and keep this sort of as a conceptual idea. But essentially, we have to define a space in which our learner can operate on our data. Right? The feature space is kind of like a lens, the lens through which we view our data. The data will sort of look different depending on the feature space we choose. In practice, though, this probably isn't the best option. By forcing a suboptimal feature space selection, it's very hard to maintain efficacy. We also lose the ability to describe our data in terms of feature vectors, which is a really convenient way to represent it, especially if the actual samples you're working with are large, or in the case of malware, they're actually dangerous. So that's one option, right? Another is to use a different learning algorithm for each classifier. This is practically very difficult, though, as there are only so many learners out there, and you can imagine it would be extremely difficult to maintain efficacy across these different classifiers. The last option is to vary the data used to actually generate the classifier. This is actually good for a lot of reasons. There's almost no bound to the number of classifiers we can generate this way. And with our feature space fixed, we can describe our samples in terms of feature vectors, something that we just stated we want to do. So we'll elect this option for achieving our desired permutation. Right? You might be skeptical about how much variation we can really achieve by doing this, right? Having different locks isn't really that helpful if the locks aren't that different from each other. And then also if we'll be able to maintain our efficacy when this data set is varying, right? And so these are both topics we'll revisit shortly and something that Ryan's going to present some results on. We also haven't even discussed the practical issues of where this training is taking place, right? Off-site at the vendor location or on-site at the location of each deployment. Either of these is possible. We're going to proceed with a sort of a distributed approach where the training happens at each user location. But by no means does it preclude a centralized vendor-centric approach. There are some advantages of doing it locally, which we're going to talk about a bit later. So either would accomplish our goal. But let's talk about how we can construct these classifiers in order to achieve a moving defense, right? So how would a locksmith basically go about serving our town? And I think we'll start by just quickly illustrating the current machine learning for malware detection paradigm. This is basically, to go to the analogy again, kind of what the locksmith workshop looks like right now. So first, vendors curate a large library of known benign software and known malicious software, which are represented by these solid green and striped red balls, respectively. These data sets are often quite large, often terabytes of data and millions of samples. Vendors then add their secret sauce, right? Whatever features they're going to use, their particular algorithm of choice, and train a learner to recognize the difference between samples in these data sets. The result is a black box, this classifier, which is the lock in our earlier analogies. The classifier accepts previously unseen files as input and issues determinations on them as benign or malicious. So the vendor can take this classifier, this is basically their value, and push it out to user environments where it's exposed to previously unseen files and again makes these determinations. These unknown samples are displayed in orange here. We'll note, though, that the samples in the user environment are labeled as orange even after the classifier makes its determination. And that's because we don't actually have access to ground truth here, right? Where we really have no choice but to trust the classifier's judgment. And different classifiers might make different determinations on the same samples. And unfortunately, none is perfect, as we already described. So we'll revisit this shortly. But returning to our original idea, generating a new lock in the lab is actually fairly straightforward. We can just use different data. And it's probably going to be hard to see in the animation, but if you look on the left, you can basically see we can change the underlying data, we'll get a different classifier, which is a different lock. We can push out that new lock to somebody else. But we now ask the question, so what's the best way then to instantiate moving defense in practice across many user environments? So we already decided we were going to use varying data input to vary our classifiers, but there are many choices still on how we can actually vary that data input. So you can imagine the simplest is probably just to use the vendor as a data source. They already have all this data lying around. Randomly select, for example, among data provided by the vendor. Perhaps maybe in some intelligent way we could age off old data and generate classifiers this way. But this doesn't really provide significant diversity in our data sets, right? We're drawing from the same source. And so we're probably not going to achieve, you can imagine, our idea of this really robust moving defense because the locks may not be that different from each other. And it's unlikely that the vendors would even be willing to provide this service, right? This would be, talking about logistical nightmares, this is high on that list. So we can probably do better than this. We could instead use a local data source, right? We can use the data that's locally, uniquely seen by each deployment and feed back the data labeled by the classifier back into our data set. And recall that we need labeled data to do this. This does help make the classifier unique, but it only reinforces what the classifier already knows, or really what the classifier thinks it knows. Right? We already just talked about the classifier's knowledge is imperfect. And if we sort of lift the veil here, we can see that we're feeding back some incorrectly labeled samples into our data set. And again, we're just reinforcing whatever imperfect knowledge the classifier already has. And so we think we can still do better than this. So what about using the local data source, but feeding back in errors, correctly labeled samples? This requires analyst or user review, a trusted user review, to determine which samples were wrongly sorted. But users and analysts are already making these truth determinations over the course of using the tool, whatever it is, and we don't need to be exhaustive. We can just take whatever labeled samples they already have. We can provide fresh, informative samples to the learner and introduce this new knowledge to the learning model. The resulting classifiers are tailored to a particular environment and stronger on the type of content that they've been seeing, and possibly even more effective than the original factory shipped version. But perhaps even more important, the resulting classifiers are unique. And so now everyone will be using their own locks, right? So we're going to select this option for the remainder of the talk, which we're dubbing in situ learning for the locality of its data source. Then we know that any of these would be feasible to achieve our goal of a moving defense. What's particularly exciting about an in situ approach is that we're not just allowing people to buy different unique locks, but we're actually basically making everybody a locksmith, right? So I'll turn it over to Ryan to give a little bit more detail on some more design decisions.
So as we mentioned, the concept of in situ is fairly simple, but there are many different factors to consider when trying to operationally implement this idea. And here we discuss two different dimensions, this idea of balanced versus unbalanced, or replacement versus addition, to consider when determining how to incorporate the additional local data into the original training set. So the first option is you have balanced replacement, in which an equal amount of benign and the malicious training set is replaced with new data. There's unbalanced replacement, in which you only replace samples in one of the old training sets with new data. Balanced addition, where an equal amount of new data is added to both the benign and the malicious training sets. And unbalanced addition, in which you only add new data to one of the old training sets. So why would you choose one versus another operationally? So looking at balanced versus unbalanced, you might choose to balance your addition of new data to prevent the classifier from favoring one class over another just because there's more of it. This might not be a major issue when only slightly imbalancing the training sets, depending on the algorithms and approaches used for training your classifiers. But this is certainly a concern as more and more data is added to only one training set in the model. Looking at replacement versus addition, there are a couple operational impacts to consider. If you choose a replacement strategy, you more quickly bias the model to the new in situ samples. However, you do this at the cost of losing part of the original training set. If you use an addition strategy, you typically increase the time required to train the new models, as well as increase storage requirements for storing those new samples. So for our experiment, we tried all four approaches. We did not see any significant differences when only adding or replacing files up to 20% for a single branch off the base model. As a result, we chose unbalanced addition for the purposes of this experiment, as it is the easiest to implement operationally due to the lack of need for additional samples or feature vectors to be provided by the vendor. So let's transition here and look at some results of our specific implementation. So the top row of this table shows the performance of the original Bayes classifier, which was trained with 20,000 benign and 20,000 malicious samples, all from the lab. The results show a false positive rate of 100% for the local data because we were testing the classifiers against the files missed by the Bayes classifier. If we had 1%, which is 200 benign files from our local data set that the original Bayes classifier missed, we see the false positive rate fall to 14%. Adding 2%, which is 400 local benign files, causes that false positive rate to fall further to 8%. And this trend continues as we add more and more local data to the original model. Therefore, we have shown that adding local data previously missed by the Bayes classifier to the in situ model results in a lower false positive rate on that local data. But the question remains, how is the performance against the original lab data set? And as our results show, there was little to no degradation in performance on the lab data. Therefore, the in situ models we generated are performing equally or better than the Bayes classifier. We can further validate this claim by generating 10 random classifiers using 5% unbalanced addition and evaluating their performance. Now, this is very similar in concept to a k-fold validation, because we ultimately want to prove that we're not just getting lucky with our specific sampling of our new data set. So to generate these classifiers, we take our original lab data set and add a random sampling of our local data that was missed by the Bayes classifier. And this results in a new classifier, R1, or trial number 1. This can be repeated using a different random sampling for our local data to generate R2, or trial number 2, and so on and so forth for R3 through R10. And it's important to note that these classifiers were generated using the same local data source for this experiment. But in reality, these 10 classifiers can represent 10 different operational environments, each with their own data sources. So looking across all 10 classifiers, the results show that performance is very consistent with standard deviations of roughly 0.5%. This means we are generating classifiers that have equal or greater effectiveness compared to the Bayes classifier. In other words, we are producing equally effective locks. But the question remains, are these locks fundamentally different from the base lock shipped by the vendor? So averaging across the 10 in situ models that we just generated, compared to the Bayes classifier, we use two different metrics to try and capture model commonality. The first measure is something we call utilized feature space commonality. This is specific to our specific implementation of the machine learning models. So when we are training our models, we have our total feature space, which was down selected in the lab from the global feature set. This total feature space is on the order of tens of thousands of features. So only a subset of these features are actually used by the learner when generating a new model. Therefore, the commonality here is defined as the overlap of these subsets divided by the sum of the feature subsets. And this measure ends up being about 30% and is very consistent across all 10 of our models. The second measure we employed is more general and can be applied to any machine learning approach. And it's something we call overlapping misclassifications. So every classifier, as we know, makes mistakes. And we are trying to capture if the in situ mistakes are the same or different compared to the Bayes classifier. So we tested both classifiers against the same set of 10,000 samples that were not used for training. The subset misclassified by each model, which ends up being about 3%, is shown in the circles of the Venn diagram. And the commonality is defined as the overlap of these subsets divided by the sum of the misclassification subsets. And this measure ends up averaging around 46%, and again, is very consistent across all 10 of our models. So using these two metrics, we feel fairly confident that our in situ models are significantly different from the Bayes model. But are we just forking these models in the same direction? Or are they all being forked in different directions? And so to answer this question, we can look at a pairwise comparison of all the randomly generated in situ models using our overlapping misclassifications metric. Now there are a lot of numbers here, so let me explain what is going on first instead of focusing on the exact numbers themselves. So first, let's look at a comparison of R1 and the R2 classifiers. So we've already established R1 is different from the Bayes. And we've also established R2 is different from the Bayes. What we don't know is how R1 differs from R2. So in this graphic, the forward slashes represent the files missed by R1, which in reality are about 3% of the total samples analyzed. And the backwards slashes represent the files missed by R2. Again, roughly 3% of the total samples. Where these slashes intersect are the files that are missed by both classifiers, or about half of that 3%. And we can repeat this comparison for the R2 and R4 classifiers, with the intersection again showing the files that are missed by both models. So what this means is that any two given in situ classifiers have a roughly 50% overlap in misclassifications out of the 3% that each of them miss. In other words, this means of the misses, half the time they are missing the same files, but half of the time they are not. It's important to re-emphasize that each of these in situ classifiers represent different deployments. Therefore, you are gaining diversity across all of those deployments. Therefore, these locks are not just different from the original lock, but are also significantly different from one another. So now we can revisit our original demo and introduce 4 new targets that are using 4 of our previously generated in situ models. So let's see what happens when we deploy the variant that defeated the original machine learning model against the new in situ models. So in this video, we have overlaid a label of which in situ model out of 4 we are testing, as well as a real-time kill count to see how many of the models were successful and how many were defeated. And these 4 in situ models in reality, as I mentioned earlier, represent 4 different operational deployments that have all been trained on their own local individual data. It's important to note that both the original antivirus and machine learning software missed this variant. So any protection we can demonstrate here would be a major improvement over the existing deployments. And it's also important to realize that these models are not perfect. As you can see here, one of the in situ models was, in fact, defeated. So to summarize, in the first part of the demo, we showed that the attacker had obtained a copy of the machine learning software and had iterated until they had found a variant and that had defeated it. In the second part of the demo, we introduced 4 new targets that were all running in situ models that were branched off of the original machine learning model. And here we show that 3 of the new in situ models caught the threat, but the 4th did still miss it. However, again, it is important to re-emphasize that if these 4 targets had all been using the base model, all 4 would have been compromised. So you might argue that if we're holding out these different data sources for these in situ classifiers, we should just combine the data and generate an even better classifier. And it's possible that performance would be marginally better overall. But that's missing the point. We need to consider the attacker's perspective. Any marginal improvement in performance would be at the cost of significantly reducing uncertainty for the attacker. While the new in situ approach is not a magic bullet, you've at least created a defense through diversity that increases the risk of the attacker being exposed.
Thank you. So, to recap, the use of in situ learning provides many benefits, right? It provides a diversity of defense spatially across deployments, as well as temporally. Additionally, training on local data allows for construction of environment-specific classifiers, which, among many other benefits, allows for increased performance on the type of data observed by that deployment, as we saw in our results. I should also mention that the results we showed here were for the purposes of this experiment, but we've actually seen this also in our real deployments that I mentioned at the beginning of the talk. So I know there are a lot of other questions you may have about how this can be deployed operationally. We only have so much time, but we'd be happy to talk about that afterwards as well. An in situ approach also provides increased responsiveness for users. Right? Using the traditional deployment method, if the machine learning solution is repeatedly hitting on the same false positives, or maybe even worse, is repeatedly missing the same false negatives, the only opportunity to improve the classifier is to submit those samples to the vendor and basically cross your fingers that your sample will be incorporated. And that'll be incorporated into either some custom model that they're providing you, or worse, and probably more likely, into the global model that they're sharing with everybody. So the only short-term alternative for a user then is really to fall back on sort of a brittle signature or rule matching-like approach to either ignore or flag the file as needed. In situ allows this data to be incorporated into the model directly and immediately. And finally, there is no need to share personally identifiable or proprietary data to improve classifiers. I should emphasize here, this is not an argument against data sharing or threat intelligence sharing in general. But aside from a user or enterprise's desire to share and the occasional technical hurdles in doing so, as many people in this room are probably aware, there are situations where it's very difficult or even illegal to share certain types of data without excessive modification. So for example, PDFs that have personal information, files with proprietary company information, or classified files of any kind. An in situ approach allows this intelligence to be incorporated into the machine learning model rather than having to discard it or rely entirely on the vendor's data or willingness to implement a custom solution. And so I'll leave you with a wall of text summarizing the sort of big picture. Right? We saw that improvements in machine learning methods for malware detection are weakened by the reliance on this traditional deployments paradigm. A dedicated attacker need only obtain an arbitrary copy of the security solution to break through the target with confidence. We also saw that the concept of a moving defense addresses this shared model vulnerability and may be naturally applied to some machine learning solutions. We discussed just a few of the many ways of achieving moving defense using machine learning, and settled on several design decisions that were both easiest to operationalize and yielded best results. But as we saw, there are many different ways of doing this, and we hope that vendors may actually recognize ways of applying this to their own technology. And last, that this diversity offered by moving defense is better for the herd. I don't mean this in the way that Alex Pinto was talking about physical contact and herd immunity yesterday, but that if we all use identical defenses, we're all worse off for it. And changes in the security industry don't just come about because of changes in the tactics of adversaries, right? That's something else we saw, but because of the resulting demand from users. And so if I return to the locksmith example one more time, if we as townspeople are happy with our identical locks, then identical locks is what we're going to get. And so I'll leave you with this admonition. We all need some understanding of the technology that's underlying our security products, and we should challenge practices seen across the industry. Right? It should not just be about what your security vendor is and is not telling you. So, thank you. I think we have probably a minute or two for questions. We've been asked if you could actually use the mics. I think there's one right in the center over there. Or you can yell it out if you have to. Sure. Sure, so the question was, if I heard you right, what was the difference between the unbalanced and the balanced training sets we had? I'll probably let Ryan speak to that.
The unbalanced and the balanced really refers to how you're adding the new local data into your model. So if you're going to add, say, 100 benign files to your original training set, a balanced approach, you would also want to add 100 additional malicious files. And so those might be files that you need to pull from the vendor, or they might be files that you've curated locally.
Right.
And the idea is to try to prevent the training sets from getting severely unbalanced.
Right. And the reason we mentioned that we opted for the unbalanced approach because it was easier, essentially, was that you can imagine it's probably annoying to enforce this equal balanced training list on user environments, right? If users are seeing a lot of false positives but not false negatives, you would need to provide a way to ship them additional malware, basically, or malicious feature vectors in order to balance out their training set.
Yeah, and we found it didn't really vary too much up to when you're adding up to 20%, but we did have some internal data that showed, when you're starting at 40, 50%, you might want to look at more of a balancing approach.
Okay, and at the mic?
Hi, great talk. My question is, if we assume that this becomes kind of the industry standard approach, great. Have you given any thought to how you would constrain the model on the local system to kind of sanity check that it hasn't forked too far off of your original base?
Yeah, sure. So there's that kind of comes down to what test sets you're using. Mm-hmm. So as we saw in our results, one thing we were evaluating on was our original lab test set.
Right.
And so that's a really good way to make sure that even if, again, you've achieved this different lock idea, that you haven't lost your efficacy, right, on your original test data.
So you would ship the user's local model back to your lab to
No,
reevaluate it on your own training set?
Yeah, it's kind of an operational question. So one way to do that, if you can imagine having some sort of secure sharing mechanism where you could ship those classifiers back, you could additionally provide a way of testing on that original lab data by providing that instead the other way, where the vendor provides that to the user.
Right.
You could ship it in the form of feature vectors, or some sort of reduced
Okay.
file set.
Okay, great. Yeah, you mentioned 20% and you were still achieving good results. So that's quite robust already, but interesting long term. Thank you.
Great, thank you. Let me see, do we have another minute? I don't know. Yeah, I think we can take
One more
more question at the mic again.
Okay, thanks for the talk. I had a question. Could we achieve this diversity in defense using a multi-scanning solution, such as VirusTotal?
Sorry, repeat that one more time.
Like
Right here.
diversity in defense, right? Having variety of logs, achieving that using a multi-scanning engine
Oh, I see.
service like VirusTotal, where they scan it with a lot of AVs.
Right. I don't know. I can speak to that, or if you want to.
Yeah, I mean, you can achieve some diversity. So, I mean, you do have some diversity in the security marketplace with different vendors. But the reality is that's limited. You only have, say 40 or 50 AV solutions out there. And really, out of those, only a handful are widely deployed.
Right.
So,
And I'll actually interject that if you look at a lot of malware code that's been released, often there's actually switch statements that actually specifically handle each one of those different AV solutions, for example, right? So it's a good idea and it's important to have, but it's on its own probably not quite sufficient to really get after this really robust moving defense that we're talking about. And I think that's all the time we have, but we'll be hanging out if we can find a spot out in the hallway if you have any more questions. So thank you.
thank you.